Right now, the entire solar system is sailing into a region of space we have never crossed before. Our sun, every planet, and every living thing on Earth is moving through a cloud of interstellar gas that is hotter and denser than anything we have traveled through in recorded human history. The magnetic shield the sun generates around us, our only real protection against the radiation of deep space, is responding to that new environment in ways scientists are still scrambling to understand. We will go through the shrinking boundary, the ice age connections, the radioactive iron buried in the ocean floor, and the moment Voyager crossed into something no probe was built to survive. The solar system has never stayed still. Right now, the sun is carrying Earth and every other planet through interstellar space at roughly 51,000 miles per hour. We have been moving for 4.5 billion years, and for the last several tens of thousands of years, we have been traveling through a relatively quiet, thin pocket of gas called the local interstellar cloud. Scientists confirmed something recently that changes everything about that picture. We are no longer fully inside the familiar region we mapped and modeled. We are crossing into something different, something we do not fully understand yet. This is confirmed science, backed by data from multiple space agencies. The solar system is entering a new patch of interstellar material, and the transition is already happening. The edge of our sun's protective bubble is responding to it right now, in ways instruments are actively measuring. To understand why that matters, picture the solar system as a ship. The sun is the engine. Everything it throws outward, a constant stream of charged particles called the solar wind, inflates an enormous bubble around us. That bubble stretches far beyond the last planet, out past where any spacecraft has ever been sent, and it separates us from the raw, unfiltered environment of interstellar space. For billions of years, that bubble has been our shield. Everything outside it is a different world entirely. Now picture that ship sailing into a region of thicker water. The pressure from outside pushes back harder. The bubble compresses. What was once a wide, comfortable buffer starts tightening. That is the situation scientists are currently watching unfold in real time. The data did not come from a single dramatic discovery. It built slowly. Telescopes measured the density and temperature of the gas ahead of us. Satellites tracked changes in particle flow at the boundary of our bubble, and the Voyager probes, launched in the 1970s and now billions of miles away, began sending back readings from the actual edge that did not match what the models predicted. Scientists had to revise their understanding of the boundary itself, then revise it again. Here is the detail that hits hardest. The cloud we are entering is not homogeneous. It does not have a smooth, gradual density. It has pockets, filaments, variations that could shift conditions abruptly rather than slowly. We are not sailing into calm, predictable water. We are sailing into something with its own internal structure, and we are doing it blind, from the inside, with instruments that were built before we knew this crossing would happen. For most of human history, the sky above us looked fixed. Stars moved in predictable arcs. The universe felt static, distant, and irrelevant to daily life. The idea that Earth itself is physically entering new cosmic territory, that the environment of space surrounding our solar system is actively changing, breaks that picture completely. This is a transition event, and transitions in physics are where the strange things happen. The next question scientists are wrestling with is exactly how different this new region is from what we have known. The answer involves temperature, density, and magnetic fields that behave in ways our models were not built to handle. And that is what makes the next piece of this story genuinely unsettling. The sun is doing something extraordinary every single second. It is exploding, slowly, continuously, in every direction at once. A stream of charged particles, protons, electrons, and helium nuclei blasts outward from the sun's surface at speeds exceeding 1 million miles per hour. Scientists call this the solar wind, and it never stops. Day and night, solar minimum and solar maximum, The sun pours this stream into space in all directions simultaneously. The solar wind does something remarkable as it expands. It carves out territory. As it pushes outward, it creates an enormous region of space where the sun's influence dominates over everything outside. That region is called the heliosphere. It is a bubble, roughly spherical, though scientists debate the exact shape that extends well beyond the orbit of Neptune, far past the edge of the planetary system most people picture when they think of our solar system. The heliosphere is our shield. Every cosmic ray, every energetic particle fired by distant exploding stars, every charged fragment of interstellar debris that moves through the galaxy hits the heliosphere first. Most of it deflects. Most of it never reaches Earth. The heliosphere absorbs the punishment so we do not have to. To get a sense of its scale, imagine Earth as a marble sitting inside a bubble the size of a sports stadium. The walls of that stadium are the outer edge of the heliosphere, where the solar wind finally loses the fight against the pressure of interstellar space. That outer edge is called the heliopause. It is the true boundary between our solar system and everything outside it. Past the heliopause, the sun's wind stops. Interstellar space begins. Inside the stadium, Earth sits in a relatively protected zone. Cosmic radiation still reaches us. The heliosphere does not block everything, but it filters out the most energetic and dangerous particles. Satellites and astronauts operating within this bubble are still exposed to radiation, but at levels that life on Earth evolved alongside. Outside the heliopause, the numbers change dramatically. The radiation environment of true interstellar space would overwhelm any unprotected biology within a short time. Here is the piece most people have never been told. The heliosphere is not a fixed structure. It breathes. It expands and contracts with the sun's activity cycle. During solar maximum, when the sun is more active and throws out stronger winds, the bubble swells. During solar minimum, it pulls back. And critically, the external pressure from interstellar space also pushes in. As the solar system moves through regions of higher or lower gas density, the heliosphere responds accordingly. Scientists confirmed that over the past few decades, solar wind pressure has actually been dropping. The bubble is smaller than it was 50 years ago. Meanwhile, the material outside is getting denser as we move into the new cloud. Both things are happening simultaneously. The shield is weakening at exactly the moment the environment outside it is intensifying. The stakes for life on Earth are direct. Galactic cosmic rays, the high-energy particles, the heliosphere filters, affect atmospheric chemistry, cloud formation, and over very long timescales, mutation rates in living organisms. A compressed heliosphere means more of those particles get through. How compressed? How much more gets through? Those are the questions scientists are urgently trying to answer. And the first clue came from a place no one expected. Something started changing in the 1990s that scientists did not fully recognize until they had decades of data to compare. The solar wind, the constant outward stream that inflates the heliosphere, began weakening. The pressure it exerted at the outer boundary dropped measurably. By the early 2000s, instruments confirmed it. The heliosphere had shrunk. The outer boundary had pulled inward by a distance that, in human terms, sounds enormous, but in cosmic terms, represented a real and meaningful compression of our shield. This was confirmed. Multiple satellites, multiple research teams, independent measurements, all pointed to the same trend. The solar wind is not a simple, steady stream. It carries magnetic field lines from the sun's surface, spun out into a spiral pattern as the sun rotates. That spinning magnetic field adds structure to the heliosphere, creating layers and boundaries within the bubble itself. When the wind weakens, those layers shift. The whole architecture of the shield changes. The immediate consequence is a change in how well the heliosphere deflects incoming galactic cosmic rays. These are subatomic particles, accelerated to near light speed by distant explosions, supernovae, colliding neutron stars, black holes consuming matter. They carry enormous energy. When the heliosphere is healthy and strong, it deflects a significant portion of the most energetic ones before they reach the inner solar system. When the heliosphere compresses, the filtering becomes less effective. Scientists measured the increase. Galactic cosmic ray intensity inside the heliosphere rose during the period of solar wind weakening. The numbers were real. The change was detectable not just at the edge but at Earth's orbit. Here is where the story becomes genuinely strange. The compression is not happening evenly. The heliosphere has a nose, the direction the solar system is currently moving toward, which faces into the oncoming interstellar material, and a tail, which stretches behind us like a wake. The nose compresses more than the tail because the pressure from the new cloud hits it directly. This creates an asymmetric shield, one side more exposed than the other. Picture walking into wind. Your front takes the pressure, your back stays relatively sheltered. The solar system is doing exactly that. The leading edge of the heliosphere, the side currently pushing into the denser cloud we are entering, is facing the highest external pressure. Scientists are watching that nose region with particular attention because it is the first part of the shield to feel the full effect of the new environment. And the solar wind's weakness is not temporary. The trend has continued. Some solar physicists are actively debating whether the sun itself is in an unusually quiet period, or whether something about its interaction with the new interstellar environment is suppressing the wind's strength. Those two explanations have very different implications. If the sun is simply in a quiet phase, the heliosphere could reinflate during the next activity cycle. If the interstellar environment is genuinely affecting the sun's output, the situation could persist or worsen over timescales that matter to civilization. There is a third possibility, one that connects our shrinking shield to a pattern buried deep in Earth's geological past. A pattern so alarming that when scientists first proposed it, many colleagues refused to take it seriously. The local interstellar cloud is an actual structure in space. It has boundaries, a measurable temperature, a density, and a magnetic field orientation that differs from the field inside the heliosphere. Scientists have mapped it from the inside, using the way it affects particles entering our solar system, using the faint glow of hydrogen and helium atoms streaming in, and using data from probes that crossed the boundary and measured conditions directly. The cloud is hot. Its temperature runs at roughly 18,000 degrees Fahrenheit. That sounds extreme, but interstellar clouds are strange objects. Despite being that hot, they are also extraordinarily thin. The density is so low that the gas would qualify as a better vacuum than anything humans can produce in a laboratory. The heat comes from the energy of individual particles moving fast, but there are so few particles per cubic inch that the overall pressure is tiny. Here is the part that matters. The cloud we are entering next appears to be denser than the one we have been moving through. The density difference is not enormous in absolute terms, but for a structure as sensitive as the heliosphere, even modest increases in external pressure produce measurable compression. Scientists have modeled what happens to the heliosphere under various density scenarios. The results range from manageable to severe, depending on how thick the new material turns out to be. The issue is that we are measuring the new cloud from inside the old one. Our instruments are looking outward through a medium that partially blocks and distorts the signal. Getting a clean reading of exactly what lies ahead is genuinely difficult. Scientists are working with incomplete information. They know the transition is real. They know the new material is denser. The precise degree remains an active area of research and, in some cases, sharp disagreement. The magnetic field angle adds another layer. The local interstellar cloud has a magnetic field that runs at an angle to the sun's own magnetic field. Where those two fields meet, at the heliopause, there is a zone of interaction where particles behave in unexpected ways. As we move deeper into the cloud, that interaction zone shifts. The dynamics at the boundary change. Models built on the old geometry need updating. One confirmed detail stands out. Astronomers detected an influx of interstellar atoms streaming into the heliosphere from the direction we are moving toward. These are actual atoms from outside our solar system: hydrogen, helium, oxygen, neon physically entering our space and passing through it. Scientists track them as a kind of continuous sample of the material we are sailing into. The composition and speed of those incoming atoms have shifted measurably over the past few decades, consistent with the solar system crossing a boundary inside the cloud structure. We are already inside something different. The material surrounding us has changed. We are not approaching a transition. We are inside one. What we do not know yet is how deep we are and what lies further in. The cloud has internal structure that our instruments can only partially resolve. Some regions within it are thicker than others. We could be near the outer edge of the denser zone, or we could be at the beginning of a long, deep passage through it. The most precise measurements we have of the boundary itself came from something nobody planned. 2 spacecraft, launched to study the outer planets, accidentally became the most important interstellar probes ever built. In August of 2012, something happened that engineers at a space agency in Pasadena, California, had been waiting decades for. A spacecraft launched in 1977, traveling for 35 years, crossed a boundary that no human-made object had ever crossed before. Voyager 1 passed through the heliopause. It entered interstellar space. The scientists watching the data that day described the moment as surreal. Instruments that had been recording the solar wind's particles for decades suddenly registered a dramatic shift. The solar wind vanished. A new population of particles appeared, particles that came from outside the solar system entirely. The magnetic field changed direction. Everything changed at once, within a relatively short stretch of its journey, confirming that the heliopause is a real, physical boundary and not a gradual fade. Voyager 2 crossed the same boundary 6 years later in a different location, and the readings were similar but not identical. The heliopause was thinner at the point Voyager 2 crossed it. The particle densities differed. The magnetic field shifted by a slightly different angle. This was a discovery in itself. The boundary is not uniform. It varies across its surface. And both probes found something that should have been expected but was still startling. The temperature of the plasma just inside the heliopause was far higher than models had predicted. Where that extra heat comes from is still actively debated. One leading theory involves the interaction between solar wind particles and incoming interstellar particles, producing a kind of friction that heats the boundary layer. Another theory suggests that galactic cosmic rays deposit energy into the region as they push inward. Scientists have evidence for both processes. The debate is about which one dominates. Here is what Voyager confirmed that bears directly on the cloud crossing. The probes measured the pressure conditions at the boundary during their crossing. Those measurements, combined with solar wind data from that period, told scientists how the heliosphere was sized and shaped at that specific moment. When researchers project those measurements forward, accounting for the weakening solar wind and the increasing density of the material ahead, the models show continued compression. Voyager 1 is now more than 14 billion miles from the Sunday. It is transmitting data on a signal so faint that it takes over 22 hours to reach Earth, even traveling at the speed of light. The science team uses the largest radio antennas on Earth just to receive it. The probe was never designed to last this long. Its nuclear power source is degrading. Instruments are being shut down one by one to conserve energy. Within the next decade or so, the last instrument will go dark. Before that happens, both Voyagers are measuring the interstellar medium at their current locations, the only physical sensors humanity has ever placed in true interstellar space. And what they are reading does not fully match the models. The particle environment, the magnetic field structure, the pressure readings, all slightly off from predictions. Each discrepancy is a clue about the actual nature of the region our solar system is moving into. One of the biggest surprises came years before either probe crossed the heliopause. It came from a satellite that was orbiting Earth, looking outward, and stumbled onto something completely unexpected at the boundary. In 2009, a satellite called the Interstellar Boundary Explorer began doing something no spacecraft had done before. Instead of flying out to the edge of the heliosphere, it stayed near Earth and looked outward, not with light, but with a type of particle called an energetic neutral atom. These are particles that form at the heliopause when fast solar wind ions collide with incoming interstellar atoms and swap electric charges. The resulting neutral particles travel in straight lines, unaffected by magnetic fields, and they shoot back inward through the heliosphere like tiny bullets. By detecting where they came from, scientists could map the shape of the boundary from the inside, like seeing a wall by watching what bounces off it. What they saw did not match any prediction. Running across the sky, roughly perpendicular to the direction the solar system is moving, was a bright ribbon of energetic neutral atoms, a concentrated band of them, far more intense than the surrounding signal, curving across the map like a scar. Scientists had dozens of models describing what the heliosphere boundary should look like. None of them had predicted a ribbon. Every single model produced a roughly uniform map. The ribbon was completely outside the theoretical framework. The discovery forced an immediate rethinking of the heliosphere's interaction with the external magnetic field. The leading explanation, still a theory as of today, not fully confirmed, is that the ribbon marks a region where the interstellar magnetic field runs parallel to the heliopause surface. In that geometry, reflected particles get trapped temporarily, bouncing back and forth before finally escaping inward, which concentrates their signal into a narrow band. But this explanation requires the external magnetic field to have a very specific orientation, one that differs from earlier estimates. What the ribbon tells us about the cloud crossing is significant. The interstellar magnetic field outside our heliosphere is structured in ways we did not anticipate. If the field has unexpected concentrations and orientations, then the way it interacts with the heliosphere as we move into denser material will also be harder to predict. The ribbon is a map of a force we cannot fully see yet. There is another implication. The ribbon's brightness changes. Scientists have watched it shift over multiple years of observation. The changes correlate partly with the sun's activity cycle, but not perfectly. Something in the external environment is also contributing to the variation. As the solar system moves, the angle between the heliosphere and the external field changes slightly. The ribbon responds. The map is updating in real time. Some scientists believe the ribbon could serve as an early warning system. If the interstellar material ahead becomes significantly denser, the ribbon's signal should change in predictable ways before the full compression reaches the inner heliosphere. The satellite is still operating, still watching, still sending back maps that no model fully explained. The boundary is stranger than anyone thought, and the shape of the bubble itself, which scientists assumed they understood, turned out to be one of the most fiercely contested questions in modern astrophysics. What the debate over that shape revealed changes everything about how exposed we actually are. The most urgent question scientists face about the cloud crossing is also the hardest one to answer with precision. How long will we be inside this denser region? How long until conditions change enough to measurably affect Earth? The answers span an enormous range, and the disagreement between researchers is genuine and unresolved. The solar system moves through space at roughly 51,000 miles per hour. That sounds fast. On a cosmic scale, it is a crawl. The local interstellar cloud itself is enormous. The solar system entered its current region of the cloud somewhere between 45,000 and 150,000 years ago. Estimates vary because the boundary was not sharp everywhere, and the cloud has internal structure. Getting out the other side, if conditions remain similar, could take another 10,000 to 20,000 years or more. But the relevant question for what happens to Earth's environment is different from the question of when we exit the cloud entirely. The relevant question is how the density varies along our path through it. If the new, denser region we are entering now is a thin layer, conditions could stabilize within a few thousand years. If the denser material extends deeply along our trajectory, the compression of the heliosphere could intensify over timescales that matter on a civilization scale. Here is what makes the timeline genuinely alarming to some researchers. Certain models suggest the most significant effects on the heliosphere do not build gradually at all. They suggest there are threshold conditions, specific density and pressure levels, where the heliosphere's behavior shifts abruptly rather than proportionally. Below the threshold, the shield compresses but holds. Above it, the dynamics change qualitatively, not just in degree. Scientists are currently uncertain whether the material we are moving into reaches those thresholds. The confirmed data shows clear changes over the past 50 years. The heliopause has shifted inward. Cosmic ray flux has increased inside the heliosphere. Interstellar atoms, flowing into the solar system, have changed in composition and speed. These are all measured, documented facts. The trend is real. The unknown is whether the trend continues at its current rate, accelerates, or eventually stabilizes. That depends on what the next 10,000 miles of our path through the cloud looks like. And right now, the instruments we have cannot resolve that clearly. A small group of researchers takes a more urgent position. They argue that the combination of weakening solar wind and entering denser material creates a compounding effect that could significantly alter Earth's cosmic ray environment within a time frame of centuries, not millennia. This view is a minority position in the scientific community, and it remains unconfirmed. But the researchers who hold it point to specific measurements that the mainstream models have difficulty explaining. Most scientists land somewhere in between. They treat the crossing as a long-term process worth monitoring carefully, with potential effects becoming more noticeable over thousands of years. The consensus, to the extent one exists, is that this is serious enough to study intensively, but unlikely to produce dramatic changes within a single human lifetime. That consensus assumes the new region does not contain any particularly thick or energetically charged pockets of material. Assumptions about what we are sailing into have already been wrong once before. The ribbon was the first proof. The geological record is the second. Galactic cosmic rays are the most energetic particles in the known universe. Some of them carry more energy in a single subatomic particle than a professionally thrown baseball. They come from every direction, fired by supernovae, pulsar winds, and collisions between neutron stars across distances of thousands of light years. Most of them never reach Earth's surface. The heliosphere blocks a portion. Earth's magnetic field deflects more. The atmosphere absorbs the rest, turning them into cascades of secondary particles that shower down from above but mostly lose their punch before reaching the ground. The key word in all of that is mostly. When cosmic ray flux increases, the cascade of secondary particles that reaches the lower atmosphere changes in intensity. Scientists have confirmed this effect by comparing cosmic ray measurements with atmospheric chemistry data. The particles interact with nitrogen and oxygen molecules in ways that produce nitrogen oxides. Those compounds affect ozone chemistry directly. A sustained increase in cosmic ray intensity, maintained over decades or longer, can measurably alter the ozone layer's thickness. A thinner ozone layer means more ultraviolet radiation reaching the surface. The biological effects of elevated ultraviolet radiation are well documented. Mutation rates in organisms increase. Phytoplankton in the surface ocean, which produce a significant portion of Earth's oxygen and form the base of the marine food chain, are particularly sensitive to ultraviolet increases. A major suppression of phytoplankton productivity would ripple through the entire ocean ecosystem. There is a second effect that scientists believe is also real, but are still actively researching. Cosmic rays appear to play a role in cloud formation. High-energy particles ionize air molecules in the lower atmosphere, and those ions act as seeds for cloud droplets. Experiments have demonstrated the ionization effect in controlled conditions. The scale of its influence on actual global cloud cover is debated, but several research teams have found correlations between cosmic ray intensity and certain types of low-altitude cloud coverage in historical data. If cosmic ray flux increased enough to significantly increase low cloud coverage, the climate implications could be substantial. Low clouds reflect sunlight back into space. More of them means less solar energy reaching the surface. Less solar energy reaching the surface means cooling. Over timescales of centuries, this is a plausible mechanism for climate shifts linked to space environment changes. The numbers matter enormously here. A modest increase in cosmic ray flux, within the range of what the heliosphere's current compression might allow, produces effects that are real but subtle. A larger increase, the kind that deeper cloud penetration might eventually produce, could push those effects into ranges that show up clearly in the geological record. And here is the key connection. Scientists have gone looking in that record. They have found things there that are difficult to explain by any mechanism other than a change in Earth's cosmic ray environment. Isotopes produced almost exclusively by cosmic ray interactions with the atmosphere, preserved in ice cores and ocean sediments, show distinct peaks and valleys that match no volcanic or solar pattern. The record is there. The question is, what caused the variations? And one candidate has a very specific address in our galaxy. Scientists have known for a long time that ice ages do not follow a simple rhythm. Earth has cycled in and out of major glacial periods for hundreds of millions of years, and the pacing is irregular in ways that orbital mechanics alone cannot fully explain. The standard model involves changes in Earth's orbit and axial tilt, which alter how much sunlight different regions receive across thousands of years. That model works reasonably well for the most recent ice ages. For the longer patterns stretching back hundreds of millions of years, it leaves significant gaps. In the 1980s and 90s, a different hypothesis emerged. A team of astronomers noticed that the timing of major climate shifts and mass extinction events in Earth's fossil record seemed to correlate with the solar system's movement through the spiral arms of the Milky Way galaxy. The galaxy's arms are regions of higher star density, more active star formation, more supernovae, and crucially, higher concentrations of dense interstellar clouds. Every time the solar system passed through or near a spiral arm, conditions for life on Earth appeared to worsen. This idea is still theoretical. Confirming it requires matching orbital mechanics of the entire solar system through galactic arms with the timing of events in the fossil record over hundreds of millions of years. The uncertainties in both measurements are large, but the correlation has enough consistency that the hypothesis remains actively studied. What is confirmed, and this is important, is that Earth's geological record contains deposits of a specific radioactive isotope called iron-60 that should be essentially absent on Earth. Iron-60 is produced almost exclusively inside stars. It arrives on Earth only when a nearby supernova explosion throws stellar material across interstellar space. Multiple layers of iron-60 have been found in ocean floor sediments, at depths corresponding to roughly 2 million years ago, and also around 8 million years ago. The deposits confirm that something exploded near enough to our solar system to litter Earth's ocean floors with stellar debris. Those same time periods show up in the fossil record and climate proxies as periods of increased stress on marine ecosystems. The correlation is not proof of causation, but it is a data point serious scientists take seriously. The direct connection to cloud crossings comes from a different direction. Researchers have looked at specific transitions in Earth's paleoclimate record, periods where global temperature dropped sharply and ice coverage expanded quickly, and asked whether the timing aligns with the solar system moving through denser regions of the local bubble, the larger structure our solar system has been traveling through for roughly 14 million years. Some analyses find alignments that are difficult to attribute to coincidence. Others find the data too imprecise to draw firm conclusions. The most striking proposed connection involves a cold period that began roughly 2 million years ago and reshaped ecosystems across the planet. Some researchers argue this timing aligns with the solar system entering a denser filament of interstellar gas, the same type of transition currently underway. The argument is that increased cosmic ray flux compressed cloud layers and reflected sunlight, cooling the planet into a new glacial cycle. The debate is not settled. Geological time is imprecise, but the proposed mechanism is physically coherent. and the evidence from iron deposits confirms that interstellar material does reach Earth during certain periods. If past cloud crossings left marks in the sediment layers of Earth's ocean floors, the current one might be doing the same thing right now. And the region of space we have been sailing through for the past several million years. The giant cavity that shaped our journey is itself a product of ancient violence. About 14 million years ago, something catastrophic happened in our region of the galaxy. A series of massive stars, dozens of them, reached the end of their lives in rapid succession and exploded as supernovae. The blasts were so powerful and so clustered in time and space that they carved an enormous cavity in the interstellar gas surrounding them. They pushed the dense gas outward in an expanding shell, leaving behind a vast region of extremely hot, extremely thin plasma. That cavity is called the local bubble. Our solar system has been sailing through the interior of that bubble for the past several million years. The bubble extends roughly 1,000 light-years across in some directions. It is lined with a shell of compressed gas, the material the old supernovae shoved aside, and that shell is still expanding today, slowly and steadily, though the energy driving it has mostly dissipated over millions of years. Living inside the local bubble has been profoundly good for life on Earth. The interior of the bubble is thin. The density of interstellar gas within it is far lower than in the surrounding galaxy. That means less external pressure on the heliosphere, a larger and more robust shield, and lower cosmic ray flux reaching Earth. Some scientists argue that the unusually stable cosmic environment inside the bubble contributed to the conditions that allowed complex life, and eventually intelligence, to develop on Earth over the past several hundred million years. The local interstellar cloud, the cloud our solar system has been crossing, exists inside the bubble. It is a patch of denser gas suspended within the larger thin region. Think of the bubble as an enormous, mostly empty room. The local interstellar cloud is a fog bank hanging inside that room, and our solar system has been passing through it. Here is the extraordinary part. The bubble itself is not isolated. It connects to a network of other supernova-carved cavities extending across our region of the galaxy, a structure researchers have mapped using ultraviolet and X-ray observations. Our local bubble sits within this interconnected foam of hot, thin regions, surrounded by denser walls of gas. The geometry of those walls and cavities shapes which direction our solar system is heading into, and how the interstellar material along our path varies. Confirmed data shows our solar system is currently near one of the inner edges of the local bubble, moving toward a denser boundary region. The thin, protective interior is behind us. The compressed shell, where gas density rises and the interstellar environment intensifies, lies ahead. Scientists have used pulsar timing and dust mapping to trace the shape of this boundary and confirm our trajectory relative to it. The era of sailing through the bubble's quiet interior is ending. Millions of years of relative cosmic calm, defined by the aftermath of ancient stellar explosions, are giving way to something harder to predict. The walls of the room are approaching, and the walls themselves carry the fingerprints of something scientists found in an extremely unlikely place, the bottom of the ocean. At the boundary of the heliosphere, two magnetic fields meet. One belongs to the Sunday. It spirals outward with the solar wind, carried billions of miles from its origin, stretched and twisted by the rotation of the sun into a shape something like a spinning pinwheel. The other belongs to interstellar space. It threads through the galaxy on an enormous scale, shaped by the remnants of ancient supernovae, the rotation of the Milky Way, and forces that operate across hundreds of light years. These two fields are oriented differently. They approach the heliopause at an angle to each other, and where they meet, the physics becomes complicated in ways that took scientists decades to begin understanding and still produce disagreements today. Magnetic fields do not simply stop at boundaries. They interact. Where two fields of different orientations meet, a process called magnetic reconnection can occur. Field lines snap and reconnect in new configurations, releasing energy and accelerating particles to high speeds. This process happens on smaller scales in Earth's own magnetic environment during geomagnetic storms. At the heliopause, it happens across a boundary millions of miles thick, driven by two enormous and differently structured fields. The consequences matter for Earth. Reconnection events at the heliopause can temporarily open channels through which interstellar particles flow more easily into the heliosphere. These are brief, localized events, but they create fluctuating corridors of reduced shielding. Scientists detected signatures of reconnection in the Voyager data. The events were real, measurable, and more frequent than early models had predicted. As the solar system moves into denser interstellar material, the external magnetic field's pressure on the heliopause increases. The geometry of where and how the two fields meet changes. Models suggest this could increase the rate and intensity of reconnection events at the boundary, creating more frequent periods of temporarily elevated cosmic ray access to the inner solar system. The misalignment angle between the interstellar field and the Sun's field is not fully pinned down. Measurements from multiple satellites and from the Voyager probes give slightly different estimates, and reconciling them requires modeling assumptions about the structure of the field through regions we cannot directly measure. The ribbon discovery complicated this further because the ribbon implies the external field has specific orientations that differ from earlier estimates in important ways. What scientists agree on is that the interaction zone is not passive. The heliopause is an active, dynamic boundary that is doing real physics constantly. The solar wind hits interstellar material there, slows, and piles up in a region called the heliosheath. Interstellar particles push back. Reconnection events create bursts of accelerated particles in both directions. The whole system is in constant motion. As external pressure builds from denser material, the heliosheath, the buffer zone between the solar wind's last push and the true boundary, compresses. The margin gets thinner, and thin margins, in physics, mean more extreme behavior at the boundary itself. What happens when cosmic rays flood through that boundary in greater numbers has effects far above Earth's surface, in a layer of atmosphere most people never think about. But the particles that survive the journey all the way down leave a signature that biologists are beginning to find very interesting. A galactic cosmic ray is a subatomic particle that has been accelerated to a speed so close to the speed of light that the difference is almost meaningless. The most energetic ones detected carry the equivalent energy of a baseball thrown at nearly 60 miles per hour, concentrated into something smaller than an atom. They travel across thousands of light years, carving through magnetic fields, bouncing off dense gas clouds, slowly losing direction but not energy, until they reach our solar system. Most cosmic rays are atomic nuclei. Protons are the most common. Helium nuclei follow. Then heavier elements like carbon, oxygen, and iron, stripped of their electrons by the violence of their acceleration. A small fraction are electrons. The rarest are antiparticles produced in extreme environments near black holes and neutron stars. They come from everywhere. The galaxy is full of sources, the remnants of stellar explosions scattered across thousands of light years, the jets of matter fired by active galactic nuclei, regions where pulsar winds pump particles to extreme energies. Some of the highest energy cosmic rays appear to originate from outside the Milky Way entirely. When one of these particles enters Earth's atmosphere, it collides with a nitrogen or oxygen nucleus high above the surface. That collision is catastrophically energetic. The original particle shatters, and its energy converts into a cascade of secondary particles, a shower of pions, muons, electrons, and gamma rays spreading outward as they fall. By the time the cascade reaches sea level, it is spread across an area potentially thousands of feet wide, but the individual particles carry only a fraction of the original energy. Most are harmless to biology at typical exposure levels. The heliosphere filters cosmic rays through two mechanisms. First, the solar wind's magnetic field scatters lower energy particles, deflecting them before they reach the inner solar system. More of these mid-range particles get through. Their flux at Earth's orbit increases measurably. Satellites measuring cosmic ray intensity have tracked this relationship for decades. During solar minimum, when the heliosphere contracts slightly, cosmic ray counts rise. During solar maximum, they drop. The relationship is confirmed. What scientists are watching now is a longer-term version of the same effect, driven by the cloud crossing rather than the solar activity cycle. For organisms on Earth's surface, the current increase in mid-range cosmic ray flux is within the range of natural variation. The concern is about compounding changes over longer timescales, and for anyone venturing beyond Earth's additional magnetic protection, like astronauts on deep space missions or future lunar settlements, the numbers are already significantly more serious. The records of what these particles did to life in the past are written in a place scientists have been studying for decades. The answers from that record are stranger than most people realize. One of the most unsettling aspects of the cloud crossing is what scientists have learned about the internal structure of interstellar clouds. From a distance, a cloud like the one we are entering might look smooth and uniform, the way a fog bank looks from an airplane. Up close, and the Voyager data has given scientists a taste of what up close means here. Interstellar clouds are turbulent and uneven. The local interstellar cloud contains filaments of denser gas, pockets where the material concentrates more than in surrounding regions, boundaries inside the cloud where conditions shift over relatively short distances. Scientists have mapped some of these internal variations using the signatures they leave on ultraviolet light passing through the cloud from distant stars. The mapping is imprecise. Our viewing angle from inside the cloud limits what we can resolve, but the variations are real and confirmed. The implications for the heliosphere's behavior as we move through the cloud are significant. If the solar system moves through a relatively thin patch of the cloud, the heliosphere might maintain something close to its current size. If we enter a denser filament, compression could intensify rapidly. The transition between these conditions could happen over timescales of thousands of years, which is gradual in geological terms, but extremely abrupt in the context of the stable environment life on Earth has enjoyed. Here is what makes this genuinely difficult to predict. The solar system is moving through the cloud at tens of thousands of miles per hour. The cloud itself is also moving in a different direction. The relative motion between our solar system and the cloud material means we are not simply traveling through a stationary medium. We are moving through something that is itself flowing. The effective density we encounter at any given time depends on both our speed and direction and the cloud's own internal velocity structure. Scientists call these velocity differences between the solar system and interstellar gas the interstellar wind. Spacecraft have measured it. The interstellar wind hits the heliosphere's leading edge like a real wind hits a moving vehicle, and its speed and direction affect how the heliosphere deforms. As the cloud's internal structure shifts, the effective wind speed and density vary in ways that compound the uncertainty. A transition through a particularly dense filament inside the cloud might last anywhere from a few centuries to tens of thousands of years, depending on the filament's size and orientation relative to our path. We cannot currently measure ahead of us clearly enough to know how many such filaments we might encounter, or where the densest one on our current trajectory lies. The confirmed piece is this: density variations inside the cloud are real. They exist. Our trajectory through them is active. The heliosphere is responding to whatever patch we are currently in, and both the Voyager probes and the IBEX satellite are watching the response happen in real time. What the geological record suggests about past encounters with dense filaments is what makes the next chapter genuinely hard to dismiss. The Interstellar Boundary Explorer satellite was not supposed to discover anything revolutionary about the shape of the heliosphere. It was designed to map the boundary systematically, to confirm and refine what existing models already predicted. What it found instead restructured the field. The satellite completed its first full sky map in 2009 and released the results to the scientific community. Scientists studying the map expected to see a roughly uniform distribution of energetic neutral atoms across the sky, with higher concentrations at the heliosphere's nose and lower concentrations at the tail. The ribbon was nowhere in any model. When researchers first saw the data, multiple teams independently concluded that some kind of instrument error had occurred. The signal was too strong and too structured to be natural. It was natural. Every cross-check confirmed it. The ribbon is a real feature of the heliosphere's interaction with interstellar space, and it covers roughly a third of the entire sky in the IBEX maps. Its brightness peaks vary across its length, and those peaks shift over time. The ribbon responds to changes in solar activity, but its response is delayed by years compared to what models predict, suggesting that whatever is causing it involves processes that operate on timescales longer than a single solar rotation. The leading explanation involves the angle between the solar wind and the external interstellar magnetic field, where the field lines run tangent to the heliopause. Outgoing solar wind particles that escape the heliosphere and become neutral get reflected back inward. They pile up along that tangential region, creating the observed concentration. This model matches the ribbon's general shape, but struggles with some of the time variation data. An alternative explanation suggests that particles outside the heliosphere are getting trapped in a region where the external and internal magnetic geometries create a natural confinement zone. The ribbon, in this scenario, is the glow of a particle trap operating at the boundary of our solar system. This model makes different predictions about how the ribbon should respond to changes in the interstellar environment as the solar system moves into denser material. The two models are not yet distinguishable by existing data. Scientists are using the ongoing observations, now spanning more than a decade of measurements, to try to separate them. Whichever explanation turns out to be correct tells us something different about how the heliosphere will behave as external pressure increases. What both explanations share is a dependence on the interstellar magnetic field's orientation and structure. The ribbon is a record of where and how the external field touches our boundary. As we move into the new cloud and the external field geometry changes relative to the heliopause, the ribbon should shift. Scientists are watching for exactly that shift in current data. The ribbon also revealed something about the heliosphere's shape that nobody expected. The nose of the heliosphere, the direction we are moving into, turns out to be far less prominent in the boundary structure than models assumed. The interaction is more distributed, more complex, and less predictable than the clean comet-like shape that dominated textbook diagrams for decades. The actual shape of the heliosphere, now that researchers are actively debating it, turns out to be one of the most important and unresolved questions in determining how exposed we are to what lies ahead. For a long time, scientists assumed the heliosphere was shaped roughly like a comet, a rounded nose facing the direction of motion and a long streamer of a tail stretching behind, pushed back by the oncoming interstellar wind. The image made intuitive sense. Moving through a medium creates drag on the back end. The solar wind would continue pushing outward at the rear, but slower and drawn out into a long, diffuse structure stretching far behind the solar system. That picture has been significantly revised. The revision matters because the shape of the heliosphere determines how it interacts with the interstellar medium at every surface simultaneously. And as we enter denser material, the shape determines where the first and most intense compression occurs. The first challenge to the comet model came from IBEX data. The energetic neutral atom maps showed a heliosphere that looked less elongated than the comet picture implied. The tail region was brighter and more structured than expected for a long, thin streamer. Then a separate satellite, designed for a completely different mission, confirmed something unexpected. The tail is not a smooth stream. It is structured, folded, and far more compact than the comet model predicted. The revised picture is closer to a crescent shape, though even that is a simplification. The heliosphere has lobes at the sides, pushed out by the solar wind in directions perpendicular to both our motion and the interstellar magnetic field. The front is compressed by the oncoming interstellar wind. The tail at the back is shorter and wider than expected. This matters for the cloud crossing in a specific way. In the comet model, the long tail acted as a gradual buffer at the rear. Material entering from the sides or rear would have more distance to travel before influencing the inner solar system. In the crescent or more spherical models, the geometry is more symmetric. External material presses on more of the heliosphere's surface simultaneously. The compression is more uniform, which means the inner solar system faces elevated exposure more quickly when external pressure rises. The tail question also connects to interstellar dust. Dust grains from outside the solar system, confirmed by satellite measurements, are already entering through the heliosphere's flanks and rear. In the comet model, the tail's structure would sweep some of this material away. In the rounder model, the paths dust grains take through the heliosphere are more varied. Some of them reach the inner solar system. A few reach Earth. Scientists have confirmed the dust arrivals. Particles of confirmed interstellar origin have been collected by satellites and analyzed in laboratories. Their composition matches what interstellar chemistry would predict. They are real visitors from outside our solar system, physically landing in our neighborhood. As we push into denser material, more of those visitors are expected, and some of what gets carried in by the interstellar wind is far more exotic than dust grains. Some of it is energetic enough to affect the chemistry of Earth's atmosphere in ways that climate models have only recently begun to incorporate. The most extreme scenario for what a fully compressed heliosphere could eventually allow through sits just ahead in the story, and the evidence for it does not come from models. It comes from the seafloor. In the 1990s, a spacecraft called Ulysses was studying the Sun from a unique orbit that took it above and below the solar poles. As a side mission, it carried a dust detector. What that detector recorded was unexpected. Flowing through the heliosphere, crossing through the Sun's entire protective domain, were particles of interstellar dust, actual grains of material from outside the solar system, passing through the heliopause, traveling through the heliosheath, crossing the termination shock, continuing inward, and arriving in the inner solar system where Earth orbits. The dust grains were small, microscopic, but they were physically real, and their composition was distinctly interstellar, enriched in elements like silicon, carbon, and magnesium in ratios that match interstellar chemistry rather than solar system chemistry. They were not local material, they came from outside. The quantity was not alarming. The flux of interstellar dust through the inner solar system is small compared to the local dust that dominates the zodiacal cloud. But the fact of their presence confirmed something fundamental. The heliosphere is permeable to at least some interstellar material, even in its current relatively healthy state. As the heliosphere compresses, the filtration changes. Larger grains, which the heliosphere's magnetic structure currently deflects more effectively, can penetrate more easily when the boundary weakens. The rate of interstellar dust reaching the inner solar system increases. Some of that dust reaches Earth's upper atmosphere, where it can act as nucleation sites for cloud formation and aerosol layers. Satellites have been tracking the changing flux of interstellar dust into the heliosphere over the past 2 decades. The rate has varied with solar activity, which was expected, but there is a longer-term component to the variation that some researchers connect to the changing density of the surrounding interstellar medium as the solar system moves through the cloud. More material around us means more pressure driving dust inward. The atmospheric effects of interstellar dust remain an active area of research. Individual grains have negligible direct impact. The aggregate effect of increased interstellar particle flux on upper atmosphere chemistry is something climate scientists and atmospheric physicists are only beginning to model seriously. Current models suggest the effect is small at present levels, but could become relevant if the flux increased by an order of magnitude or more during a passage through significantly denser material. There is a more dramatic confirmed example of interstellar material reaching Earth. It does not involve dust. It involves the debris of a stellar explosion preserved in the sediment layers of ocean floors around the world, waiting for scientists to find it. What they found when they drilled into those sediments is one of the most direct proofs that Earth's environment is connected to events happening across thousands of light years of space. In the 1990s, a team of scientists was analyzing manganese crust samples drilled from the floor of the Pacific Ocean. These crusts build up slowly over millions of years, layer by layer, preserving a chemical record of what fell through the ocean from the atmosphere above. The team was looking for something specific: iron-60, a radioactive isotope of iron that does not occur naturally on Earth in significant quantities. The only confirmed source of iron-60 is the interior of massive stars, where the intense nuclear reactions of stellar cores produce it. The only way it reaches Earth is through the explosion of those stars. They found it, a clear layer of iron-60 concentrated in depths of the crust corresponding to roughly 2 million years ago. The signal was distinct from background levels. The concentration was far above what any terrestrial process could explain. The layer was real, preserved in the ocean floor, deposited by material that had once been inside a star and was blasted across interstellar space by a supernova explosion within a few hundred light-years of our solar system. Subsequent research found the same iron-60 layer at sites across the globe, in the Pacific, Atlantic, and Indian Oceans. The deposit is worldwide. The event that produced it struck the entire planet simultaneously. A second, older layer was found at depths corresponding to roughly 8 million years ago, suggesting at least 2 nearby supernova events in the relatively recent past of our solar system's journey. The proximity of these events was sobering. A supernova close enough to deposit measurable iron-60 on Earth's ocean floors is close enough to have compressed the heliosphere significantly during the event, close enough to have elevated cosmic ray flux at Earth's surface for thousands of years during and after the explosion, close enough to have contributed measurably to the ozone chemistry and radiation environment at the surface during the period of deposition. Researchers cross-referenced the timing of the iron-60 layers with climate records from the same periods. The layer corresponding to 2 million years ago falls within a period of marked global cooling and expansion of polar ice. The connection is not proven as direct cause and effect. Other factors contributed to the climate changes of that period, but the overlap is specific enough that several research teams treat the supernova event as a contributing factor in the cooling rather than a coincidence. The 2 million year layer has a further significance for the current cloud crossing. Some researchers argue that the same supernova event that deposited the iron-60 may have also contributed to pushing dense interstellar gas into the path our solar system is currently traveling through. In this scenario, the cloud we are entering now is partly a remnant of the same stellar explosion whose debris sits on the ocean floor. The past and the present connect in the same cloud of gas, shaped by the same ancient violence. The ocean floor does not just carry debris from one direction, it carries the accumulated record of everything that fell from space across millions of years. And what researchers have begun to realize is that the record does not sit still. It is still being written right now. The material arriving today, falling through the heliosphere, settling through the atmosphere, drifting to the sea floor, is different in composition and quantity from what fell 50,000 years ago. We are in a new region, and the record being written in the sediments at this moment will tell scientists millions of years from now exactly when the transition happened. The sun does not behave the same way every year. It cycles. Roughly every 11 years, it moves from a quiet period of minimal activity to a peak of intense activity and back again. During active periods, the solar surface erupts with flares, coronal mass ejections, and surges of solar wind that temporarily inflate the heliosphere and drive cosmic ray flux down. During quiet periods, the solar wind weakens, the heliosphere contracts slightly, and cosmic ray counts rise. This cycle has been documented continuously since the 18th century. Scientists can trace it back thousands of years using isotopes preserved in ice cores and tree rings, the same cosmic ray-sensitive isotopes that make past interstellar events detectable. The cycle is one of the most reliable patterns in solar physics. What is far less understood is how that cycle interacts with the external interstellar environment. The two systems are not independent. They push against each other at the heliopause continuously. When the sun is active, its strengthened wind pushes the boundary outward against whatever external pressure the interstellar medium is applying. When the sun quiets, external pressure wins more ground, and the boundary pulls inward. The cloud crossing adds a third variable to this interaction. As the external pressure increases due to denser interstellar material, the same phase of solar quiet that once produced modest heliosphere compression now produces more severe compression. The timing of this interaction has a compounding problem. Solar scientists have observed that the current era of solar activity has been unusually subdued. The last two solar minimums, the quiet troughs of the 11-year cycle, were deeper and longer than historical averages. Solar maximum activity levels have also been lower than expected. The Sun is behaving more quietly than its recent historical baseline during exactly the period when the external interstellar pressure is increasing. Whether the Sun's unusual quietness is a random fluctuation within its normal long-term variability, or whether there is a physical connection between the changing interstellar environment and the Sun's output, is an open and genuinely contested question. Some solar physicists argue the interstellar magnetic field interacts with the Sun's own magnetic cycles in ways that could modulate solar activity. The mechanism is theoretically plausible. The evidence for it is indirect, and most solar physicists treat it as speculative. What is confirmed is the compounding effect in the data. Lower solar wind pressure plus higher external interstellar pressure equals a heliosphere smaller than either factor alone would produce. The cosmic ray flux increase the instruments are recording reflects both factors simultaneously. Separating their contributions requires modeling assumptions that introduce their own uncertainties. For Earth, the combined effect is what matters, regardless of which factor is driving it. And as the next set of instruments begins delivering data from closer to the Sun than any probe has ever gone, the picture of exactly how the inner solar system is responding is getting sharper in ways that are beginning to resolve some of the disagreement. What that new data is revealing about the solar wind structure changes some foundational assumptions about how robust the shield actually is at its base. The Parker Solar Probe launched in 2018 with a mission that required engineering solutions that had never existed before. It flew closer to the Sun than any spacecraft in history, passing through the Sun's outer atmosphere, the corona, at speeds exceeding 400,000 miles per hour. To survive, it deployed a heat shield that faced temperatures exceeding 2,500 degrees Fahrenheit, while keeping the instruments behind it at near room temperature. The data it returned changed the field. One of the most significant discoveries involved the solar wind's structure. Scientists had assumed the solar wind was a relatively smooth, continuous outflow, growing gradually more uniform as it expanded outward from the Sunday. The Parker probe found something different. The solar wind is full of sudden, intense reversals of the magnetic field embedded within it. Scientists named these reversals switchbacks. They appear as kinks or folds in the magnetic field lines that the solar wind carries, where the field direction flips abruptly and then flips back within a span of seconds to minutes. Switchbacks are energetic. They carry bursts of faster-moving plasma within the solar wind stream. As they travel outward, they interact with the surrounding, slower solar wind, creating turbulence that affects the wind's overall structure by the time it reaches the outer heliosphere. The heliosphere's boundary is not encountering a smooth, steady wall of solar wind. It is encountering a turbulent, structured outflow, full of embedded energy fluctuations. This matters for the cloud crossing because the heliosphere's ability to deflect interstellar particles depends on the structure of the magnetic field the solar wind carries. A turbulent, switchback-rich field is less efficient at deflecting particles than a smooth one. Some of the gaps and folds in the field created by switchback interactions allow cosmic rays to penetrate more easily, not because the heliosphere has physically compressed, but because its internal structure has become more porous. The Parker probe also confirmed that the solar wind's acceleration happens closer to the Sun than previously thought. The outer corona, just above the surface, accelerates the bulk of the solar wind to a significant fraction of its final speed within a short distance. This means the wind's mass flux and energy are set very close to the Sun, and variations in coronal conditions translate directly and quickly into variations at the outer heliosphere. During the current period of subdued solar activity, the corona's structure has been different from its behavior during more active periods. The regions of the corona that produce the fastest, most magnetically structured solar wind are less prominent. The result is a solar wind that is slower, less dense, and carries less magnetic structure per unit volume than during more active solar phases. The combination of a turbulent, porous field from switchbacks and an overall weaker wind means the heliosphere's shielding effectiveness is degraded in two distinct ways simultaneously. The physical boundary has compressed, and the internal magnetic structure that does the actual particle filtering has become less organized. What a specific deep space mission could reveal about how this affects our path through the cloud sits at the center of a debate that has fractured the planetary science community in recent years. The shape of the heliosphere sounds like a settled question. Scientists have been studying it for decades. Multiple satellites have measured its boundary. 2 probes crossed it. And yet, as of today, 2 fundamentally different models of the heliosphere's shape remain in active, unresolved competition, and the scientific debate between them has grown sharp enough to generate open criticism in the published literature. The traditional model describes the heliosphere as comet-shaped, a rounded leading edge compressed by the oncoming interstellar wind, a long, drawn-out tail stretching behind, potentially extending hundreds of billions of miles. This model dominated textbooks and visualizations for decades and was supported by early theoretical work on how the solar wind expands into a medium that has a preferred direction of relative motion. The competing model describes the heliosphere as more spherical or crescent-shaped, with a much shorter, more structured tail. This model gained ground from the Ibex neutral atom maps, which showed a heliosphere that looked far less elongated than the comet picture implied. Additional support came from a separate mission that mapped the heliosphere's tail using a different detection method and found a compact, lobed structure rather than a long streamer. The stakes of this debate are not cosmetic. The shape determines the geometry of every interaction the heliosphere has with the interstellar medium. It determines how much of the heliosphere's surface area faces the incoming cloud material directly, how much is shielded by geometry alone, and how the 2 magnetic fields meet along different parts of the boundary. A comet-shaped heliosphere has a very small cross-section facing the new cloud at any given moment. A spherical one presents its entire surface simultaneously. For the cloud crossing, this means the difference between 2 very different exposure scenarios. In the comet model, the nose compresses first, and most severely. The tail and flanks remain relatively protected for longer. The inner solar system has a longer period before elevated cosmic ray access affects Earth's orbit region. In the spherical model, the compression is more symmetric. The whole boundary moves inward more uniformly, and the effect on the inner solar system arrives more quickly. Teams that support each model have published responses to the other's evidence. The debate has produced detailed rebuttals, counter-analyses, and calls for new observational data to break the deadlock. The community has not reached consensus. Each camp has respected scientists and rigorous published work on its side. What both models agree on is that the heliosphere is responding right now to something changing outside it. The disagreement is about geometry, not about the existence of the change. And the specific particles that cross through whatever shape the heliosphere actually is have a confirmed presence here on Earth right now that most people have never been told about. The heliosphere has a confirmed leak. Scientists knew it in theory for decades, but the proof came from a mission called Stardust, launched in 1999 to collect cometary dust. The spacecraft carried a collector designed to capture particles moving through space. When scientists analyzed the samples returned to Earth in 2006, they found particles with a chemical signature that could only have originated from outside the solar system. 7 particles were confirmed as interstellar in origin. 7 actual physical samples of material from the space beyond our heliosphere, collected by a spacecraft, returned to Earth and analyzed in a laboratory. Their composition matched predictions for interstellar dust grains, silicon, oxygen, iron, and sulfur in combinations that reflect interstellar chemistry rather than solar system chemistry. Their trajectories, reconstructed from the collector geometry, confirmed they had entered from outside. 7 particles sounds trivial. The significance is that they confirmed the physical reality of what theory had long suggested. The heliosphere does not block everything. Interstellar dust grains with sufficient size, composition, and approach angle can penetrate the heliospheric magnetic structure and travel all the way to Earth's orbit. The heliosphere is a filter, not a wall. More recently, the Cassini spacecraft, orbiting Saturn for over a decade, also detected interstellar dust particles using its own instruments. Saturn orbits far from Earth but well within the heliosphere. The particles reaching Saturn's orbital distance are smaller than the ones that could reach Earth, because the heliosphere's filtration is more effective at excluding larger grains at inner distances. But their confirmed presence at Saturn's orbit, well inside the outer heliosphere, means the penetration of interstellar material is not limited to a thin skin near the boundary. The flux of interstellar dust entering the heliosphere tracked by satellites has changed over time. The change correlates partly with solar activity and partly with longer-term shifts in the surrounding interstellar environment. Scientists can separate these contributions using data spanning multiple solar cycles. The longer-term component shows a trend consistent with the solar system encountering changing interstellar material as it moves through the cloud. What enters with the dust matters as much as the dust itself. Interstellar gas atoms, hydrogen, helium, neon, oxygen, also stream through the heliosphere. Scientists call this the interstellar wind, and they have measured it precisely. The direction and speed of the interstellar wind relative to the solar system tells scientists exactly what cloud material they are currently embedded in. Over the past several decades, that direction has shifted slightly, and the measured properties of the incoming atoms have changed, confirming that the solar system is moving through a changing interstellar environment. The atoms streaming in are largely harmless individually. The dust grains are too sparse to matter at current levels. The radiation carried by cosmic rays riding the same interstellar wind is where the biological story gets serious. And the place where that story is most directly relevant, right now, today, is somewhere far above Earth's surface, where physics becomes personal. Scientists describe the current situation as a change in degree. The heliosphere is smaller than it was. More cosmic rays are getting through. The effect is real and measurable. But the scale of change so far remains within a range that life on Earth's surface would not notice directly. The ozone layer is intact. The radiation reaching the ground has increased modestly. The chemistry of the upper atmosphere has shifted slightly. Nothing catastrophic has happened. The question researchers are actively modeling is what happens if the compression continues and intensifies. Specifically, what does Earth's environment look like if the heliosphere contracts to a small fraction of its current size? This is a theoretical scenario, one that requires denser interstellar material than what we have confirmed is immediately ahead. But the physics of it is real, and understanding the end point of the process is critical for understanding the stakes. In the most extreme scenario considered by serious models, a heliosphere compressed by a factor of 10 or more would no longer extend significantly beyond the inner planets. The heliopause would sit somewhere close to or inside the orbit of Saturn. The shield that currently deflects galactic cosmic rays before they reach Earth's orbital distance would provide almost no protection for Earth specifically. Galactic cosmic ray flux at Earth's surface would increase enormously. The ozone layer under those conditions would face sustained destruction by the nitrogen oxide chemistry that cosmic ray cascades drive. Satellite modeling of a complete ozone layer collapse suggests ultraviolet radiation at the surface would increase to levels lethal to most surface organisms within years, not centuries. Phytoplankton, the foundation of the ocean food web and a major source of atmospheric oxygen, are the most sensitive. Their collapse would cascade through every ecosystem connected to the ocean. This extreme scenario requires a cloud density far higher than current measurements show in our immediate path. Scientists are clear about that. The scenario is a theoretical bound on the worst case, not a prediction. The confirmed data describes a moderate compression over geological timescales, not a catastrophic collapse within any humanly relevant timeframe. What the extreme scenario does is establish the mechanism with clarity. The heliosphere is the reason complex surface life on Earth is possible at all. Its existence is not a coincidence, it is a prerequisite. Any process that significantly reduces it changes the fundamental radiation environment that biology depends on. The moderate version of this, where cosmic ray flux doubles or triples over thousands of years, rather than collapsing overnight, has a biological story of its own. And that story has been playing out across evolutionary history in ways scientists are now beginning to connect to the pattern of interstellar crossings. What one group of researchers found when they overlaid the history of cloud crossings with the history of rapid evolutionary change in the fossil record is something that forces a complete rethinking of what drives biological innovation on Earth. The galaxy contains interstellar clouds across an enormous range of densities. At the thinnest end are regions like the interior of the local bubble itself, so sparse that a cubic inch of space contains fewer atoms than the best laboratory vacuum humans can create. At the densest end are molecular clouds, enormous dark structures where gas and dust pack tightly enough to collapse under gravity and form new stars. The densest molecular clouds are millions of times denser than the thin medium of the local bubble. The local interstellar cloud we are crossing sits in the moderate range of interstellar cloud densities. It is about 100 times denser than the interior of the local bubble, but vastly thinner than any molecular cloud. By the standards of the galaxy's diverse environments, it is a relatively gentle medium. Most of the galaxy's volume is filled with materials similar to or thicker than the local interstellar cloud. In cosmic terms, the local bubble interior was an unusually protected environment, and the cloud we are entering now represents something closer to a galactic average. That context matters. The conditions that Earth's biosphere evolved in, sheltered inside the local bubble for millions of years, were exceptionally favorable by galactic standards. The heliosphere did not need to work as hard in that thin environment. As the solar system moves toward conditions more representative of the typical galactic medium, the heliosphere is encountering pressures that test it more seriously than anything in recent geological history. The denser region within the local interstellar cloud that the solar system is entering now has a measured density estimated at roughly 10 times higher than the surrounding cloud material. That is a real, confirmed difference, not a theoretical projection. 10 times the density means 10 times the external pressure on the heliosphere, which, in the models, produces a compression that reduces the heliosphere's radius by a substantial fraction. For context, consider what the densest clouds in the galaxy would do to a heliosphere like ours. In a dense molecular cloud, the external pressure would be so overwhelming that any stellar heliosphere would be compressed to within the planetary system itself, leaving no effective shielding for the planets. Stars deep inside molecular clouds have essentially no heliospheric protection. Their planets, if they have any, are bathed in the full interstellar radiation environment continuously. We are nowhere near that scenario. The cloud we are entering is gentle by the galaxy's extreme standards, but understanding where we sit on that spectrum helps calibrate what is happening. The change from where we were to where we are going is real. It is measurable, and it represents a shift toward conditions that are more typical and more demanding than anything recorded in the deep human past. Whether biological systems respond to this shift in ways that show up in the evolutionary record is a question that connects the physics of interstellar clouds to something far more intimate, the history of life itself. For most of the history of evolutionary biology, the forces that drove biological change were understood to be entirely terrestrial. Natural selection, operating on genetic variation produced by random mutation, environmental pressures from climate, competition, predation, and geography, the ocean, the land, the atmosphere. The arena of evolution was Earth, and the forces shaping it came from within and from the Sunday. That picture is being expanded. A growing group of astrobiologists is now asking whether the interstellar environment, specifically the variation in cosmic ray flux, as the solar system moves through different interstellar regions, has contributed to the pace and direction of biological evolution across geological time. The proposed mechanism is direct. Cosmic rays penetrate biological tissue and damage DNA. At current flux levels, this damage is a source of the background mutation rate that all organisms experience. Most mutations are neutral or harmful. A small fraction are beneficial. Evolution depends on that small fraction. Now, if cosmic ray flux doubles or triples during a period of cloud crossing or heliospheric compression, the background mutation rate increases across all organisms simultaneously. More mutations means more genetic variation. More variation means more raw material for natural selection to work with. This does not mean more cosmic rays make evolution better. Most of the extra mutations are harmful, causing cancer, developmental errors, and reduced fitness. But across an entire biosphere, over thousands of generations, an elevated mutation rate produces a wider spread of variation. In stable environments, that extra variation mostly gets eliminated. In rapidly changing environments, the same variation can include organisms pre-adapted to new conditions. Here is the provocative part. Several research teams have looked at the timing of significant evolutionary transitions in the fossil record and compared them with estimated periods of elevated cosmic ray flux based on geological proxies like the isotopes preserved in ice and sediment. Some alignments appear. Periods of rapid species diversification in some lineages correlate with periods of estimated higher cosmic ray flux. The correlations are not perfect, and the uncertainties in both the fossil record timing and the cosmic ray proxy data are significant. The hypothesis is not consensus science. Many evolutionary biologists treat it with skepticism, pointing out that the fossil record is full of apparent correlations that dissolve under closer scrutiny, and that the causal chain from cosmic rays to evolutionary change involves too many steps and confounding factors. The cosmic ray argument requires the effect on mutation rates to be large enough to matter above the noise of all other evolutionary forces, and demonstrating that is difficult. What makes the hypothesis worth taking seriously is not any single correlation. It is the confirmation that the mechanism is real. Cosmic rays do damage DNA. Flux does vary with the solar system's environment. The heliosphere is the filter that modulates the flux. A solar system in a denser interstellar region faces a measurably different biological environment than one in a thin region. Whether that difference was large enough at past crossings to show up in the fossil record as accelerated evolution is a legitimate scientific question, and it is a question that connects directly to what a particular space telescope has been mapping across the entire observable sky. The Fermi Gamma Ray Space Telescope has been mapping the sky in gamma rays since 2008. Gamma rays are the most energetic form of electromagnetic radiation produced by the most violent processes in the universe. Matter annihilating with antimatter, particles accelerated to near light speed, exploding stars, and the extreme environments near black holes. From Earth's orbit, the sky in gamma rays looks dramatically different from the familiar optical sky. What Fermi revealed about our galactic neighborhood has direct implications for understanding the energetic environment the solar system is navigating through. The galactic center glows intensely in gamma rays, as expected, but Fermi also found something unexpected: enormous lobes of gamma-ray emission extending above and below the galactic plane, far beyond the disk of stars, reaching tens of thousands of light-years into intergalactic space. These are called the Fermi bubbles, and they represent evidence of an enormous outburst from the Milky Way's central black hole in the relatively recent galactic past. The bubbles are still inflating. They carry energetic particles outward from the galaxy's center. The relevance to our solar system's current position is subtle but real. The Fermi maps reveal the distribution of cosmic ray sources across our galactic neighborhood. They show where energetic particle production is concentrated, which regions of the galaxy are pumping the most high-energy radiation into the interstellar medium, and how the local bubble and its surrounding wall of compressed gas fit into that larger energetic picture. Our solar system sits in a region of the galaxy where the cosmic ray background is moderate by galactic standards. The local bubble provides some additional shielding from cosmic ray sources embedded in the denser surrounding gas. As the solar system moves toward the bubble's edge and eventually into denser gas beyond, its position relative to the galaxy's cosmic ray source distribution changes. The angle and distance to the nearest concentrations of energetic sources shifts. The Fermi maps also confirm something about the nature of the interstellar magnetic field in our galactic region. The distribution of gamma rays from cosmic ray interactions with interstellar gas reveals the field structure across scales much larger than any direct measurement could cover. The field in our region of the galaxy runs roughly parallel to the galactic plane, but with local variations near bubble walls and cloud boundaries that can redirect cosmic rays in complex ways. Understanding this larger magnetic architecture helps scientists model how cosmic rays travel through the interstellar medium before reaching the heliosphere. The path a cosmic ray takes from its source to our solar system is not straight. Magnetic fields deflect it, cloud density slows it, and the overall structure of the galaxy's interstellar medium shapes its journey. Fermi's maps provide the large-scale framework that smaller-scale measurements of the heliosphere boundary can be placed within. The picture emerging from combining Fermi data with heliosphere measurements is of a solar system that is not just passively drifting through space. It is actively navigating a complex energetic landscape, and the landscape itself is changing around it in ways that feed directly back to what is happening at the heliopause right now, in real time. The heliopause is not sitting still. At this moment, the outer boundary of the solar system is flexing, rippling, and shifting in response to the combined pressure of the solar wind from inside and the interstellar medium from outside. Scientists are watching this happen in real time, using data from multiple instruments simultaneously. The most direct measurements come from the Voyager probes, which crossed the heliopause and are transmitting from the other side. Voyager 1 is in interstellar space. Voyager 2 is in interstellar space. Both are continuing to move outward, and both are detecting variations in the plasma density and magnetic field around them that reflect the changing conditions at the boundary they crossed years ago. One of the most striking results from Voyager's interstellar measurements is the detection of plasma oscillations. These are waves in the charged gas of interstellar space that carry information about density changes. Voyager detected a series of these oscillations, driven by energetic events on the Sun, sending pulses outward through the heliosphere that eventually crossed the heliopause and set the outside medium ringing like a struck bell. By timing the oscillations, scientists calculated the density of the interstellar plasma immediately outside the heliosphere. The density measurements outside the heliopause are higher than the pre-mission models had predicted. The interstellar plasma in our immediate neighborhood is denser than scientists expected based on earlier estimates of the local interstellar cloud's properties. This revised density estimate feeds directly into calculations of the heliosphere's future size and behavior as the solar system continues moving through the cloud. The IBEX satellite, still operating after more than 15 years, has recorded changes in the energetic neutral atom maps that reflect movement of the heliopause itself. The ribbon's position and brightness have shifted. The boundaries between bright and dim regions of the map have moved. Scientists interpret these shifts as evidence that the heliopause has been rippling and repositioning in response to changing external pressure and changing solar wind output simultaneously. There is a confirmed event from 2012 that demonstrated the heliopause's dynamic nature in a dramatic way. A particularly powerful coronal mass ejection from the Sun sent a pulse of enhanced solar wind outward at high speed. The pulse reached the heliopause and pushed it outward measurably. Voyager 1, already beyond the boundary, detected the pressure wave as it crossed into interstellar space. The heliopause moved. The boundary of the solar system physically shifted in response to a single solar event. If a single solar outburst can shift the heliopause, a sustained increase in external interstellar pressure can push it inward over time. The two processes are the same physics operating in opposite directions. External pressure from the cloud does to the heliosphere what solar wind pulses do from the inside, and unlike a single solar event, the pressure from the denser cloud material is continuous. The monitoring systems watching all of this are producing data streams that feed into models updated regularly. The models are converging on a picture of a boundary under genuine, sustained, and measurable stress. Whether that stress reaches a level that requires a response from humanity depends on what scientists find when they look ahead more clearly. And right now, that ability to look ahead is limited in a way that has researchers calling for an entirely new type of observatory. The Sun is not the only star moving through interstellar clouds. Every star in the galaxy travels through space at its own speed and direction, passing through different regions of the interstellar medium over millions of years. And every star with a stellar wind, which includes the vast majority of stars, creates its own version of a heliosphere around itself. Astronomers call these structures astrospheres. Observing other stars' astrospheres provides something invaluable: the ability to see from the outside what is impossible to see from the inside. Our view of our own heliosphere is limited because we are embedded in it. We can measure conditions at specific points where we have sent probes, and we can map certain particle populations from Earth orbit, but we cannot take a picture of the whole structure from outside. Other stars' astrospheres can be imaged, at least partially. They show up in ultraviolet and X-ray observations as regions of interaction between the stellar wind and the surrounding interstellar medium. Astronomers have detected astrospheres around several nearby stars by observing the Lyman alpha ultraviolet emission from hydrogen piled up at the astrospheric boundary. The same process happens at our own heliopause. Seeing it around other stars lets scientists test their models of heliospheric structure against real observed examples. What these observations reveal about the range of possible heliosphere sizes and shapes is striking. Stars with stronger winds in thin interstellar environments have enormous astrospheres, extending far beyond what our own heliosphere reaches. Stars with weaker winds in denser environments have compact astrospheres, pulled tight by external pressure. The variation in size across different stellar environments spans more than an order of magnitude. Some stars have been caught in the act of moving through denser interstellar patches. Their astrospheres show visible compression on the leading side, exactly the asymmetric compression predicted for a stellar system entering a denser medium. The compressed leading edge creates a brighter bow shock in ultraviolet observations. Some of these bow shocks have been imaged in detail, and they match the geometry that models predict for our own heliosphere's leading edge as it pushes into the cloud we are entering. The most directly relevant comparison comes from stars with solar-like luminosity and wind properties, moving through cloud environments similar in density to the one we are entering. Their astrospheres provide observational benchmarks for what our own heliosphere should look like at various stages of compression. The comparisons support the models showing sustained compression. They also reveal something the models did not fully anticipate. The leading edge bow shock can become turbulent as compression intensifies, creating a more chaotic and less effective particle barrier than a smooth boundary provides. Turbulent boundaries let more particles through. More particles through means more cosmic ray access to the inner system. And the kind of access that a turbulent, compressed heliosphere allows has an effect on something that controls the daily experience of every person on Earth's surface: the weather. The phrase interstellar weather sounds like a metaphor. Scientists are beginning to treat it as a technical description. The interstellar medium surrounding the heliosphere is not a uniform, static environment. It has structure, flow, variation, and turbulence that changes on timescales ranging from decades to millions of years. As the solar system moves through it, the conditions the heliosphere encounters shift in ways that are not fully predictable from inside the system. The analogy to weather works at multiple levels. In Earth's atmosphere, weather is driven by uneven heating, rotation, and the complex fluid dynamics of air masses interacting with each other and with the surface. In the interstellar medium, analogous processes operate on vastly larger scales. Supernova shockwaves drive turbulence through the surrounding gas. Magnetic field reconnection events release energy that accelerates particles and heats local regions. Stellar winds from nearby stars press against the boundaries of interstellar clouds, creating compression and rarefaction waves that travel through the medium at speeds of tens of miles per second. The cloud we are entering has its own internal turbulence spectrum. Scientists have inferred this from the variation in interstellar absorption lines seen in the spectra of distant stars observed through the cloud. The lines fluctuate in ways that reveal velocity variations across the cloud's interior, density irregularities, and turbulent eddies at scales ranging from thousands of miles to light years. The cloud is not calm, it is moving within itself. For the heliosphere, this internal cloud turbulence means that the external pressure the boundary faces is not constant. It fluctuates. A region of slightly higher density passing by the heliosphere exerts more pressure for the duration of the encounter. A rarefied region provides temporary relief. The heliosphere breathes in and out in response, on timescales of decades to centuries, driven by the cloud's internal turbulence pattern. What scientists cannot currently do is forecast this variation. To predict interstellar weather, they would need a detailed three-dimensional map of the cloud's density, velocity, and magnetic field structure resolved on scales small enough to matter for the heliosphere over the next few thousand years. They have a rough map of the cloud's large-scale properties. The small-scale structure that determines year-to-year and century-to-century variation in the heliosphere boundary is essentially unmapped. This is the radar problem. A sailor navigating into a storm benefits enormously from radar that shows the structure of the weather system ahead. Scientists navigating the solar system through interstellar cloud structure are essentially radar blind. They can measure what the heliosphere is experiencing right now, infer recent history from geological proxies, and project general trends from large-scale cloud maps. They cannot see what specific patch of cloud material lies directly ahead on the solar system's trajectory over the next few thousand years. The variation could be favorable. The solar system could be approaching a thinner pocket within the cloud, where the heliosphere stabilizes or partially recovers. Or it could be approaching a denser filament, where compression intensifies. The instruments to distinguish these possibilities do not yet exist. They would require a new type of observatory, one operating from a location and with capabilities that have no current equivalent. What that observatory would need to be able to see and what it would tell us about our situation is the subject of one of the most important proposals currently circulating in the planetary science and astrophysics communities. Most discussions of cosmic ray effects focus on the extreme end: catastrophic ozone loss, mass extinction, civilizational collapse. Those scenarios require conditions far beyond what current measurements suggest is imminent. The scenario worth examining seriously, because it falls within the range of what the cloud crossing could actually produce over the next few thousand years, is a sustained doubling of galactic cosmic ray flux reaching Earth's surface. A doubling is not dramatic by the standards of science fiction. Biologically, its effects would be subtle at first and cumulative over generations. The background radiation dose received by organisms at the surface would increase. At current cosmic ray flux levels, an organism at sea level receives a small but measurable dose of cosmic ray-derived radiation annually. Doubling that dose would not cause immediate health effects in any individual. The change would be well within the range of natural variation across different latitudes and altitudes on Earth today. The biological significance plays out across populations and generations. Cancer risk associated with ionizing radiation increases with cumulative dose. Across a population exposed to elevated cosmic ray flux over thousands of generations, the statistical increase in mutation-driven disease would be real. The magnitude depends on which organisms and which tissues, because some are far more radiation sensitive than others. Single-celled organisms reproduce quickly enough that the increased mutation rate produces measurable evolutionary change within centuries rather than millennia. Cloud formation chemistry is where some researchers expect the most visible near-term signal. The ionization of air molecules by cosmic ray cascades affects the nucleation of cloud droplets, particularly in the lower troposphere. Studies of historical cosmic ray variation using proxy data have found correlations with cloud cover changes that, while debated, are physically plausible. A sustained doubling of cosmic ray flux could increase low-altitude cloud cover by a few percentage points. Low-altitude clouds are efficient reflectors of sunlight. A few percentage points of additional cloud coverage, maintained globally over centuries, represents a measurable reduction in solar energy reaching the surface. Climate models project a cooling effect from this mechanism, the scale of which varies significantly across different model assumptions about cloud physics. The effect would work in the same direction as reduced solar output, and the two could combine. Atmospheric chemistry changes would include elevated nitrogen oxide production from cosmic ray cascades, which reacts with ozone. The ozone layer would thin modestly. Ultraviolet penetration at the surface would increase by a small but measurable amount. Marine surface ecosystems, particularly phytoplankton, are sensitive to ultraviolet changes. A sustained increase in surface ultraviolet would reduce phytoplankton productivity in the upper ocean layer, affecting the biological carbon pump that moves carbon dioxide from the atmosphere to the deep ocean. None of these effects, individually, would register as a crisis within a human lifetime. Across 1,000 years, their accumulation would show up clearly in climate records and biological surveys. Across 10,000 years, the trajectory of Earth's biosphere could diverge measurably from what it would have been without the cosmic ray increase. The generation that first detects the clear signal of these changes coming from the heliosphere's interaction with the cloud will be the generation that has to decide whether to do anything about it. What the options for doing something actually look like is the domain of one of the most unconventional conversations currently happening in planetary science. Voyager 1 and Voyager 2 were designed to study the outer planets: Jupiter, Saturn, Uranus, Neptune, 4 worlds in sequence, reachable because of a rare alignment of the planets that made a gravity-assisted grand tour possible. The mission was expected to last roughly 5 years. The Jupiter encounters happened in 1979. Saturn followed. Voyager 2 continued to Uranus and Neptune. By the time Neptune slipped past in 1989, the primary mission was over. The probes kept going. The nuclear power sources on board, small generators that convert heat from radioactive decay into electricity, had more life in them than the mission required. Scientists turned off instruments no longer needed, routed power carefully, and kept the remaining sensors running. The probes, moving at speeds of roughly 35,000 miles per hour, continued outward through the solar system and eventually beyond it. The scientific return from the extended mission has been extraordinary. Data from the helios sheath, the transition region between the outer solar wind and the heliopause, answered questions that no model had addressed properly. Data from the crossing of the heliopause itself, in 2012 for Voyager 1 and 2018 for Voyager 2, provided the first direct measurements of true interstellar space. Data from the interstellar medium beyond the heliopause is still arriving, still yielding surprises, still forcing updates to models. The communication challenge is extraordinary. Voyager 1 is so far away that its radio signal, traveling at the speed of light, takes more than 22 hours to reach Earth. The signal arrives with a power of roughly 2 femtowatts. A femtowatt is a millionth of a billionth of a watt. Receiving it requires the largest dish antennas on Earth, operated by networks maintained specifically for deep space communication. Engineers calculate pointing angles accounting for where the probe will be when the signal arrives, because the pointing calculation uses where the probe was when the signal left. The probes are dying. Plutonium-238, the fuel source for the power generators, decays over time. The electrical output has been dropping by roughly 4 watts per year. Instruments have been switched off systematically to keep the most important ones running. Voyager 1 currently operates with a handful of functional instruments. Sometime in the late 2020s or early 2030s, what they are finding there, and what it means for the boundary we are crossing, is something the scientists receiving that 22-hour-old signal think about every time new data arrives. There is a fundamental problem with studying the heliosphere from Earth orbit. Every observation happens from inside the structure being observed. The instruments on board satellites look outward at the heliosphere's boundary from within the heliosphere itself. The Voyager probes are beyond the boundary, but they are single points, not a network, and they are moving away from it rather than providing ongoing coverage. The result is that the scientific community has an incomplete and, in some cases, contradictory picture of the boundary they are trying to characterize. Scientists proposed a solution, a mission called the Interstellar Probe, which has been formally studied by major space agencies, would fly a spacecraft to a distance many times farther than the Voyager probes reached in equivalent mission time, using advanced propulsion concepts. At that distance, the probe would look back at the heliosphere from the outside, imaging its full structure for the first time and measuring the interstellar medium properties along a well-defined path. The science case for the mission has been described as urgent by multiple review panels. The heliosphere's shape debate, the ribbon's origin, the structure of the heliopause, the properties of the cloud material immediately surrounding the solar system, all of these require observations from outside the heliosphere to resolve definitively. Some of the most fundamental uncertainties about how exposed the solar system is to the cloud crossing cannot be answered from inside the system. The mission concept involves a spacecraft that would reach 50 to 300 astronomical units from the Sun within a human career timescale. A substantially faster journey than the Voyagers, which required decades to reach interstellar space. Achieving this requires either a gravity assist from the Sun itself, a close solar flyby using a heat-shielded spacecraft, or advanced propulsion technologies that would provide sustained thrust over a long cruise phase. A separate proposal involves a constellation of small satellites positioned at different points within the outer heliosphere and just beyond the heliopause, providing simultaneous multi-point measurements of the boundary's behavior rather than the single-point snapshots the Voyagers provide. Multiple simultaneous measurements would allow scientists to distinguish between spatial variations in the boundary and temporal variations, a distinction that current data cannot make. Both proposals face the same challenge: cost and mission duration. Deep space missions are expensive. Their return on investment unfolds over decades. The political and funding environment for long-duration space science missions has been inconsistent. The interstellar probe concept has been prioritized in major advisory reports from the planetary science community, but as of now, it has not been approved for construction and flight. The scientific community is essentially watching a process that matters enormously for Earth's long-term environment, using instrumentation designed for a different era, pointed in the wrong direction, from the wrong position. The data coming in is valuable. It is also incomplete in ways that the researchers know precisely and cannot currently fix. What some of those researchers are finding in the data they do have, connecting the interstellar environment to changes in the Sun itself, has become one of the most contested claims in contemporary astrophysics. In the world of academic science, most ideas exist on a spectrum between confirmed consensus and fringe speculation. The claim that the interstellar cloud we are entering is already measurably affecting the Sun's behavior sits somewhere in the contested middle of that spectrum. It is held by credentialed researchers with published work. It is rejected or ignored by many of their peers. The debate has not been fully resolved. and the resolution matters enormously. The argument begins with the solar wind measurements. Over the past several decades, the solar wind's density and pressure have declined in ways that exceed what the sun's own activity cycle alone would predict. The sun does vary its output across the 11-year cycle, and the longer-term variation called the grand solar minimum is also known. But some researchers argue that the specific pattern and magnitude of the recent decline is inconsistent with solar-only explanations and shows signatures of external influence. The proposed mechanism involves the interstellar magnetic field pressing against the heliopause and modifying the boundary conditions that the solar corona interacts with. In this model, the sun's magnetic environment is not determined entirely by internal dynamics. The external interstellar field, pushing inward at the heliopause, creates a background condition that propagates inward through the heliospheric magnetic field and subtly alters the corona's behavior. Changes in the interstellar environment would then appear in solar activity data as unexpected variations. The mainstream response to this argument is skepticism for two reasons. First, the mechanism requires the interstellar field's influence to propagate inward through the heliosphere in ways that solar models do not currently incorporate. Adding this coupling would require substantial revision to existing solar models, and the evidence for it remains indirect. Second, solar variability is complex enough on its own that attributing specific changes to an external cause requires ruling out all solar internal explanations, which is extremely difficult given current understanding of solar dynamics. The researchers making the interstellar influence argument point to specific data points that solar internal models have difficulty explaining. The unusual depth and length of recent solar minima, the geographic pattern of sunspot distribution during recent cycles, and changes in the solar wind's composition that do not track previous cycles cleanly. These anomalies are real and acknowledged by mainstream solar scientists. The disagreement is about whether interstellar influence is the right explanation. What makes this debate significant beyond its immediate scientific content is what it implies about how the cloud crossing affects Earth. If the interstellar environment is already influencing the sun's activity, then the sun's contribution to the weakening heliosphere is not a random coincidence coinciding with the cloud entry. It is a causal connection. The cloud is compressing the heliosphere both directly, by pushing inward at the boundary, and indirectly, by modifying the sun's output. Two mechanisms in the same direction, both active simultaneously. Mainstream science has not formally dismissed this possibility, it has simply not confirmed it. The tools to confirm or rule it out do not yet exist in their necessary form. The data needed would require decades of continued observation combined with a much more complete model of how the interstellar magnetic field and the solar magnetic cycle interact across the heliopause boundary. In the meantime, the question of what humanity could actually do about any of this, the monitoring, the preparation, the scale of response a prolonged, dense cloud crossing would require, is the question that brings everything together into the most important conversation of all. Every chapter of this story has been about a process unfolding on timescales longer than a human life. The heliosphere's compression, the cloud crossing, the elevated cosmic ray flux, the potential climate and biological effects, all of these play out over thousands to tens of thousands of years. That timescale creates a specific kind of challenge for any civilization trying to respond. The first and most immediate need is measurement. The single greatest obstacle to understanding the cloud crossing is the incompleteness of current data. Scientists know the transition is real. They know the direction and general properties of the material we are entering. They do not know the internal structure of the cloud along our specific trajectory, the precise rate at which the heliosphere will continue to compress, or the threshold conditions that would produce the most significant effects on Earth's environment. Closing those gaps requires missions. The interstellar probe concept, or something like it, provides the outside view of the heliosphere that fundamentally cannot be obtained from within. A network of outer heliosphere sensors, placed at strategic positions from the inner heliosheath to just beyond the heliopause, would give scientists the simultaneous multi-point data needed to track the boundary's behavior across its full extent. Ground-based and orbital telescopes capable of mapping the immediate interstellar medium in higher resolution than currently possible would chart the terrain ahead. These are achievable goals with existing or near-future technology. They require funding decisions and political prioritization, given that the process being monitored affects the long-term habitability conditions of Earth. The scientific case for treating this as a priority-level investment is straightforward. The timeline for building and flying the missions, combined with the time to accumulate meaningful data, means decisions made now determine what scientists know 50 years from now. Beyond measurement, the cloud crossing raises questions about planetary-scale systems that humanity currently takes entirely for granted. The ozone layer's response to elevated cosmic ray flux is one. The current infrastructure for monitoring ozone is robust by historical standards, but it was built to track human-made chemical destruction, not the slower and more distributed effect of cosmic ray chemistry. Calibrating it for the interstellar crossing scenario requires new baselines and new modeling tools. Agricultural systems are another. If a sustained cosmic ray increase produces measurable cooling through enhanced cloud cover, the implications for food production at different latitudes are significant over a generational timescale. Civilizations that understand this risk in advance can develop resilient agricultural systems, diversified crop varieties, and production strategies that are less sensitive to climate variation. Civilizations that are caught off guard face the same disruption under much less favorable response conditions. Communication and electronics infrastructure is a third area. Elevated cosmic ray flux increases the rate at which cosmic ray cascades cause bit flips in electronic memory and computation systems. Current technology accounts for this at existing flux levels through error correction and hardened components in critical systems. A significant increase in flux would require updated hardening standards across civilian and military digital infrastructure. The lead time for implementing those changes across a global infrastructure is long, which means the planning needs to start well before the effects become severe. None of this requires invoking catastrophe. The cloud crossing is a long, slow process. The effects on Earth accumulate over timescales that allow for measured, rational response if the monitoring systems and the institutional will to act on what they reveal are in place. The window for building those systems is open right now. The solar system is in the early stages of a transition that will define the space environment Earth inhabits for the next several thousand years. The Voyager probes are out there, transmitting. The IBEX satellite is mapping. The Parker solar probe is reading the sun from the inside. The data is arriving. The picture is incomplete but growing clearer with every year. What humanity does with that picture, and how seriously the institutions responsible for long-term planetary welfare take the process currently underway, will determine whether the knowledge being assembled now becomes the foundation of genuine preparation or simply the record of something we understood too late to act on. The solar system is moving. It has always been moving. Now, for the first time, we know where we are going, and we are beginning to understand what it means.